A Chinese J-11 fighter screamed across the sky over Liaoning Province at Mach 1.8, its twin engines roaring at maximum power. Then, without warning, the left engine exploded in a catastrophic turbine failure, sending white-hot metal fragments through the fuselage. The pilot ejected seconds before the $40 million aircraft disintegrated. On the ground, investigators would discover what China had desperately tried to hide for 15 years. Their reverse-engineered copy of the F-15's legendary engine was a death trap that couldn't withstand combat power settings, destroying itself after hours of operation instead of the thousands of hours American engines routinely achieved. This is the story of the WS-10 engine, China's most expensive technological failure, and the proof that you can't steal engineering excellence.
The engine that powered air superiority. The Pratt & Whitney F-100 turbofan engine represented a revolution in fighter propulsion when it entered service powering the F-15 Eagle in the mid-1970s. Producing approximately 25,000 pounds of thrust with afterburner, nearly double what previous generation engines achieved, the F-100 gave the F-15 performance that seemed almost supernatural. The aircraft could accelerate vertically, sustain Mach 2.5 at altitude, and perform sustained 9G turns while maintaining energy. No Soviet fighter could match this combination of power and endurance. The F-100's capabilities came from cutting-edge technology pushed to limits that seemed impossible. The engine operated at turbine inlet temperatures exceeding 2,500 degrees Fahrenheit, hot enough to melt most metals. The compressor achieved pressure ratios of 25:1, squeezing air to densities that approached those of liquids. The turbine blades spun at rotational speeds approaching 10,000 RPM while withstanding stresses equivalent to hanging a car from each blade. And critically, the engine could maintain these extreme conditions for thousands of hours without failure. This reliability was the F-100's most remarkable characteristic. Early versions had teething problems, but by the 1980s, the engine routinely achieved mean time between failures exceeding 3,000 hours. Pilots could push throttles to maximum afterburner, knowing the engines would respond instantly and reliably. Maintainers could predict when components needed replacement, scheduling maintenance during convenient downtime rather than after catastrophic failures. The F-100 wasn't just powerful, it was trustworthy, a quality even more valuable than raw performance. For China's military planners, watching American air power dominate conflicts from the 1980s onward, the F-100 represented everything Chinese engines were not. Chinese jet engines, mostly copies of 1960s-era Soviet designs, were underpowered, unreliable, and short-lived. The WP-7 engine powering China's J-7 fighters produced about 12,000 pounds of thrust and required overhaul after perhaps 300 to 500 hours, 1/6 the lifespan of an F-100. Chinese pilots joked bitterly that their engines were consumables like fuel or ammunition to be used until they failed rather than maintained for long service lives. This capability gap meant Chinese fighters were fundamentally inferior in the most critical aspect, propulsion. No amount of airframe refinement or weapons improvements could compensate for engines that were weak, temperamental, and prone to sudden failure. If China wanted fighters that could match American air superiority, they needed engines comparable to the F-100. And since developing such engines through indigenous programs would take decades, the solution seemed obvious: acquire F-100 technology and copy it.
The Great Engine Heist. China's campaign to acquire American jet engine technology began in the 1990s and intensified through the 2000s. The effort was comprehensive, sophisticated, and disturbingly successful at penetrating supposedly secure systems and organizations. The campaign used multiple vectors simultaneously. Chinese intelligence operatives targeted engineers and scientists working at Pratt & Whitney, General Electric, and subcontractors involved in military engine programs. Some were Chinese nationals working in the U.S. aerospace industry who could be recruited through appeals to nationalism or family pressure. Others were non-Chinese engineers vulnerable to bribery or blackmail. The goal was acquiring not just blueprints, but the accumulated expertise that made American engines successful. The material science, the manufacturing processes, the quality control procedures. Cyber-espionage proved even more effective. Between 2007 and 2013, Chinese hackers associated with People's Liberation Army Unit 61398 conducted systematic intrusions into U.S. aerospace companies' networks, exfiltrating terabytes of data related to jet engine design, manufacturing, and testing. These intrusions, detected only after months or years of access, compromised design documents, material specifications, test results, and manufacturing procedures for multiple engine programs, including the F-100, F-110, and F-119. They weren't stealing randomly, explained a U.S. counterintelligence official during congressional testimony. They systematically targeted everything related to turbofan engine technology, combustion dynamics, turbine blade cooling, material science, manufacturing processes. They built a comprehensive picture of American engine technology by piecing together data from dozens of compromised systems. By the time we detected many intrusions, they'd already copied vast amounts of our most sensitive technical information. Academic and scientific exchanges provided another avenue. Chinese graduate students and researchers worked in American universities and laboratories where jet engine research was conducted. Some legitimately contributed to research while happening to gain knowledge useful to Chinese military programs. Others were directed intelligence assets specifically placed to access technologies. And some simply absorbed knowledge through legitimate academic work, then returned to China, where that knowledge informed military programs. By the mid-2000s, Chinese engineers possessed enormous amounts of American jet engine technology, design documents, material specifications, manufacturing procedures, test data. They had acquired through theft what would have cost billions of dollars and decades of research to develop independently. The stage was set for China to leapfrog generations of engine development by copying American designs. What Chinese leadership didn't understand was that stolen information alone wouldn't be sufficient. Jet engines are perhaps the most demanding engineering challenge in aerospace, requiring precision manufacturing, exotic materials, and accumulated expertise that can't be stolen or copied. China was about to learn this lesson in the most expensive way possible.
The WS-10 program began in the late 1980s, but accelerated dramatically after 2000 as Chinese intelligence acquired vast amounts of American engine data. The goal was ambitious: develop an indigenous turbofan engine producing thrust comparable to the F-100, approximately 25,000 to 30,000 pounds with afterburner, with similar performance and reliability characteristics. The program was assigned to Shenyang Liming Aircraft Engine Company, China's premier military engine manufacturer. Chief designer Liu Taihang, a Soviet-trained engineer who had spent his career working on Chinese copies of Soviet engines, led the technical effort. Liu understood that creating an F-100 equivalent represented a massive technological leap. Chinese engines had never produced more than about 15,000 pounds of thrust, and reliability was consistently problematic. The Americans have been refining the F-100 for nearly 30 years, Liu told his team during initial planning. They've solved countless technical problems, developed new materials and manufacturing processes, and accumulated expertise we simply don't possess. We have some of their data through various channels, but data alone won't be sufficient. We need to develop actual manufacturing capabilities that can produce components to American standards. But Liu's caution was overridden by political imperatives. Chinese leadership wanted results quickly. The program had enormous resources, funding reported to exceed $10 billion over its lifetime, and the expectation of rapid progress. Engineers who warned that development would be slow and difficult faced accusations of defeatism. The pressure was to proceed optimistically regardless of technical realities. The initial WS-10 design borrowed heavily from the F-100. Similar configuration, similar dimensions, similar operating parameters. Chinese engineers used stolen American data to inform their design choices, essentially attempting to recreate the F-100 using whatever materials and manufacturing processes Chinese industry could provide. This approach was fundamentally flawed because it assumed that Chinese manufacturing could replicate American capabilities if given proper specifications. The first major obstacle was the turbine blades, the components that extract energy from hot exhaust gases to drive the compressor. F-100 turbine blades were manufactured from single-crystal nickel superalloys using directional solidification processes that created blade structures without grain boundaries. These blades could withstand temperatures exceeding 2,500 degrees Fahrenheit and stresses that would shatter conventional materials. They incorporated internal cooling passages, channels only millimeters in diameter that circulated air to cool the blades from inside. And they were coated with thermal barrier coatings that provided additional temperature protection. China couldn't manufacture equivalent blades. The single crystal casting process required extremely precise control of cooling rates during solidification. Variations of even a few degrees would create defects that drastically reduced blade life. Chinese metallurgy wasn't sufficiently advanced to consistently produce the required superalloy compositions. The internal cooling passage drilling required specialized equipment China didn't possess, and the thermal barrier coatings needed application processes Chinese industry hadn't mastered. We're attempting to produce the most sophisticated components in aerospace manufacturing, admitted senior metallurgist Wang Feng during a technical review in 2005. Our best turbine blades are perhaps 60 to 70% as capable as American blades. They can't withstand temperatures as high, they fail after fewer cycles, and they're prone to cracking under stress. We can continue development to improve them, but matching American capabilities will take years of work. The compressor section presented different but equally serious challenges. The F-100's high-pressure compressor used titanium alloy blades designed with complex, three-dimensional geometries optimized through computational fluid dynamics. Manufacturing these blades required 5-axis CNC machining centers capable of holding tolerances measured in thousandths of an inch. Chinese machine tools were less precise, and operators lacked experience with such demanding components. The combustion section required materials that could withstand extreme temperatures and pressures while minimizing weight. The F-100 used sophisticated alloys and ceramic matrix composites that Chinese materials science couldn't replicate. Substitutes were heavier, less heat-resistant, and more prone to cracking under thermal cycling.
The testing nightmare.
The first WS-10 prototype ran on a test stand in 2002, a major milestone but one that immediately revealed the program's fundamental problems. The engine produced thrust close to design specifications, approximately 27,000 pounds with afterburner, but reliability was abysmal. Components failed rapidly under stress, requiring frequent replacement. The engine couldn't sustain maximum power for more than a few minutes without overheating or experiencing mechanical failures. "We're achieving rated thrust," reported Test Director Chen Ming after early test runs, "but we can't maintain it. The turbine blades are failing after perhaps 50-100 hours of operation. The F-100 turbine blades last 2,000-3,000 hours. Our combustor is cracking from thermal stress after limited use. The compressor blades are experiencing fatigue failures. We have an engine that works briefly at full power but can't sustain operations for mission-relevant durations." The testing program revealed systematic problems across every engine system. Turbine failures, the turbine section, operating at extreme temperatures and stresses, showed the shortest component life. Blades developed cracks within hours of high-power operation, failed catastrophically when cracks propagated, and shed fragments that damaged downstream components. The Chinese materials and manufacturing processes simply couldn't produce blades durable enough for sustained operations. Compressor issues. Compressor blades experienced fatigue cracking, foreign object damage sensitivity, and occasional catastrophic failures where blades broke loose and ricocheted through the engine. The titanium alloys used weren't as fatigue-resistant as American materials, and the blade geometry wasn't optimized for stress distribution. Combustor problems. The combustion section cracked from thermal stress, with welds failing and components warping under extreme temperatures. Chinese materials couldn't withstand the thermal cycling, rapid temperature changes from idle to full power and back without developing cracks. Bearing failures. The bearings supporting the engine's rotating assemblies experienced premature wear and occasional seizure with catastrophic results. Chinese bearing steels weren't as hard or wear-resistant as American equivalents, and manufacturing precision was inadequate for the high-speed, high-load conditions the bearings endured. Control system problems. The Full Authority Digital Engine Control, or FADEC, system that managed engine operations was plagued by software bugs, sensor failures, and inadequate response speed. Chinese electronics and software engineering lagged American capabilities significantly, producing control systems that were sluggish, reliable, and prone to entering failure modes that required manual intervention. Each problem spawned efforts to develop solutions, but solving one problem often revealed others. Strengthening turbine blades to reduce cracking increased their weight, which increased stresses on bearings and structural components. Improving combustor materials required developing entirely new alloys and manufacturing processes. Fixing software bugs in the control system revealed hardware limitations that couldn't be addressed without redesigning entire subsystems. By 2008, after 6 years of intensive development and testing, the WS-10 had achieved perhaps 500 hours of total test time across all prototypes, a fraction of what the F-100 would accumulate in normal service. And the Chinese engine's reliability remained so poor that flight testing in actual aircraft was repeatedly delayed for fear that engine failures would destroy expensive prototypes and potentially kill test pilots.
The pressure to proceed. Despite the mounting evidence that the WS-10 wasn't ready for service, political pressure forced the program forward. Chinese Air Force planners desperately wanted to end dependence on Russian engines, which were expensive, sometimes delivered late, and subject to political complications. Domestic engines, even problematic ones, offered strategic autonomy that imported engines couldn't provide. In 2009, over the objections of many engineers, the WS-10 was cleared for limited flight testing in modified J-11B fighters, Chinese-built versions of the Russian Su-27. The flight test pilots selected were experienced, skilled, and explicitly warned that the engines were unreliable and that they might need to eject on short notice. The flight test program immediately confirmed engineers' worst fears. Engines failed regularly, sometimes spectacularly, with turbine disc failures that sent fragments through the aircraft fuselage, sometimes more gradually through progressive degradation that reduced thrust and increased fuel consumption. Test pilots reported that WS-10-powered aircraft felt underpowered compared to Russian engine equivalents, that engine response was sluggish, and that they had much less confidence in the engine's reliability. Every flight felt like rolling dice, one test pilot later recounted. You'd start engines and wonder if this would be the flight where they failed. During high-power maneuvers, there was constant awareness that you might suddenly lose an engine or have one explode. The stress was enormous, not just flying the aircraft, but monitoring engines that you knew could fail catastrophically without warning. The program experienced at least 3 catastrophic engine failures during flight testing that resulted in aircraft losses. 2 pilots ejected successfully when engines failed, destroying the aircraft but surviving without serious injury. A third incident was more tragic. Major Wu Xiongming died when his WS-10-powered J-11B suffered a dual engine failure at low altitude during a demonstration flight. Investigation revealed that both engines had experienced near-simultaneous turbine failures, giving Wu no time to react before the aircraft crashed. Wu's death forced a temporary halt to the flight test program and triggered a comprehensive review. Investigators found that the engines had accumulated only about 150 hours of flight time before failure, less than 5% of the operational life an F-100 engine would achieve. The failures resulted from turbine blade cracks that had propagated undetected because inspection procedures were inadequate and because Chinese blades developed cracks far more rapidly than American equivalents. The WS-10 is not ready for operational service, the investigation report concluded. It suffers from fundamental materials and manufacturing limitations that result in unacceptably short component life and high failure rates. Continuing flight operations would put pilots at unacceptable risk while destroying expensive aircraft. The engine requires comprehensive redesign and materials development before it can be considered for service use.
The compromise and the cover-up. The investigation's conclusions created a political crisis. The WS-10 program had consumed 15 years and billions of dollars with the explicit goal of ending Chinese dependence on foreign engines. Admitting comprehensive failure would be politically humiliating and would acknowledge that China remained technologically inferior in critical aerospace capabilities. The solution was compromise and selective truth-telling. The WS-10 would enter limited service. Chinese Air Force units would receive aircraft powered by WS-10 engines, allowing officials to claim the engine was operational. But privately, operational restrictions would severely limit how the engines could be used. Maximum power settings would be limited to reduce stress on components. Flight hours between mandatory inspections would be drastically reduced, and units equipped with WS-10 engines would maintain lower readiness rates with more aircraft grounded for maintenance at any given time. "We're declaring victory while hiding defeat," one engineer said bitterly to colleagues. The WS-10 is operational in the sense that some engines are installed in some aircraft, but it's not truly operational in any meaningful sense. It can't be used the way American engines are used, it requires constant maintenance, and it fails far more frequently than acceptable. We're maintaining the fiction that we have indigenous engines, while reality tells a different story. Chinese propaganda trumpeted the WS-10 as proof of indigenous engine capability, with state media showing footage of WS-10-powered aircraft and claiming performance comparable to Western engines. But operational reality was far different. Chinese Air Force pilots expressed strong preferences for aircraft powered by Russian AL-31F engines, which, while far from perfect, were more reliable than WS-10s. Units equipped with WS-10 engines experienced maintenance burdens far higher than Russian engine equivalents, with engines requiring major overhauls after perhaps 500 to 800 hours, versus 1,500 to 2,000 hours for Russian engines, and 3,000 to 4,000 hours for American F-100s. The Chinese government continued purchasing Russian engines, even while claiming the WS-10 made imports unnecessary. Between 2011 and 2020, China purchased hundreds of AL-31F engines from Russia at costs exceeding $3 billion, a tacit admission that domestic engines weren't adequate to meet operational needs. Most troublingly, Chinese Air Force readiness rates suffered from WS-10 reliability problems. Aircraft powered by WS-10 engines showed operational availability rates perhaps 20 to 30% lower than Russian engine equivalents, meaning that for every 10 WS-10-powered aircraft on paper, only 6 or 7 of them would be mission-capable at any given time. The others would be grounded for maintenance, awaiting parts, or undergoing repairs from engine failures.
The fundamental failure. The WS-10's problems stemmed from attempting to replicate American manufacturing capabilities without possessing the industrial ecosystem that made those capabilities possible. Jet engines are products not just of individual factories, but of entire industrial systems. Material science, American turbine blades used nickel superalloys developed through decades of research, with precise compositions and processing that gave them exceptional high-temperature strength and resistance to creep and fatigue. China's material science lagged significantly. Their best superalloys were equivalent to American materials from perhaps the 1980s, 1 or 2 generations behind current technology. Precision manufacturing, American engine components, were manufactured using 5-axis CNC machines with precision measured in microns, operated by skilled machinists working from detailed process specifications. Chinese manufacturing equipment was less precise, operators were less experienced, and quality control was less rigorous, resulting in components that varied significantly from specification. Accumulated expertise. American engine manufacturers had decades of experience building increasingly sophisticated engines, learning from each generation what worked and what didn't. Chinese engineers were attempting to leapfrog this accumulated experience, making mistakes that American engineers had learned to avoid decades earlier. Supply chain quality. American engines depended on thousands of components from hundreds of suppliers, each producing parts to exacting specifications with rigorous quality control. Chinese supply chains couldn't maintain equivalent quality, resulting in components that looked correct but had hidden defects that caused premature failures. The F-100 is the product of American aerospace excellence developed over 50 years, explained a Western aerospace analyst. It incorporates materials science, manufacturing processes, and accumulated expertise that can't be stolen through espionage or copied by examining finished products. China tried to shortcut the development process and discovered that some technological capabilities can't be rushed. They must be earned through patient, systematic development.
The continuing struggle. As of the mid-2020s, the WS-10 remains in production and service, but its problems persist. China has introduced improved variants, the WS-10B, WS-10C, claiming enhanced reliability and performance. But reports from Chinese military sources indicate that reliability remains problematic,
with engines still requiring far more maintenance and experiencing far more failures than acceptable by Western standards. Chinese Air Force pilots, when speaking privately or anonymously online, express continued lack of confidence in WS-10 engines. They report that engines are more temperamental, require careful handling to avoid overstress, and simply don't inspire the trust that engines should provide. The contrast with American pilots' absolute confidence in F-100 engines, which they can push to maximum power without concern, is stark. The economic cost has been staggering. The WS-10 program has consumed resources estimated to exceed $15 to $20 billion when development costs, manufacturing infrastructure, and operational support are included. For this investment, China has produced an engine that's inferior to Russian engines from the 1980s and vastly inferior to contemporary American engines. The opportunity cost, what could have been achieved if those resources had been invested differently, is almost incalculable. The human cost includes test pilots who died testing unreliable engines, operational pilots who have been forced to fly aircraft powered by engines they don't trust, and maintainers who work exhausting hours trying to keep temperamental engines operational. Each WS-10 engine represents not just money wasted, but lives risked and quality degraded in pursuit of a capability that China's industrial base couldn't deliver. China continues developing newer engines, the WS-15 intended for fifth-generation fighters, the WS-20 for large transport aircraft, but these programs face the same fundamental challenges. Chinese materials science, manufacturing precision, and accumulated expertise remain behind Western standards. Espionage can provide blueprints and specifications, but it can't transfer the industrial ecosystem and accumulated knowledge that make advanced engines possible.
The lesson repeatedly ignored. The WS-10 story is ultimately about hubris, the belief that stolen technology could substitute for patient development of genuine capability. Chinese leadership looked at American jet engines and saw products that could be copied. What they didn't see was the industrial ecosystem, the materials science, precision manufacturing, quality control systems, and accumulated expertise that made those products possible. Jet engines are perhaps the ultimate test of industrial capability because they demand excellence in so many domains simultaneously. You can't fake material science. Either your alloys can withstand extreme temperatures and stresses, or they can't. You can't fake manufacturing precision. Either your components are machined to tolerances measured in microns, or they're not. And you can't fake accumulated expertise. Either your engineers understand from experience what works and what doesn't, or they learn through expensive failures. China attempted to shortcut this process through espionage and reverse engineering, and the WS-10 demonstrates the results. 20 years and $20 billion later, China has engines that work briefly at full power, but can't sustain operations for mission-relevant durations. They've produced engines that are less reliable than 1980s Russian technology, while claiming equivalence to contemporary American capabilities. And they've created a situation where Chinese pilots fly with less confidence in their engines than they should have, knowing that their power plants might fail catastrophically without warning. The F-100 engine that China tried to copy continues powering F-15s and F-16s worldwide, with some aircraft having accumulated more than 8,000 engine hours, equivalent to years of continuous operation. The latest F-100 variants produce even more thrust than original models while maintaining exceptional reliability.
American pilots trust their engines absolutely, confident that throttles will respond instantly and reliably regardless of conditions. The contrast couldn't be starker. American industrial excellence produces engines that last thousands of hours and inspire complete confidence. Chinese attempts to copy that excellence through espionage produce engines that fail after hundreds of hours and leave pilots wondering if today will be the day their engine quits. The lesson is clear. Technological superiority can't be stolen, only earned through long-term investment in the fundamentals that make excellence possible. China spent 20 years and $20 billion learning this lesson through the WS-10 program, and by all indications, they still haven't fully internalized it.